Hi, my name is Steve Blatt. I'm a researcher at Pompeu Fabra University in Barcelona, Spain. My presentation is about blockchain for decentralized 5G, specifically public utility overlay networks. So here's a quick schedule of the data in the presentation. I'll start by giving some background on the research and give details of this blockchain system, which we name CoNTe. That was designed specifically for operation within 5G networks to decentralize public utility services. So we've been working on this idea of the application of blockchain in wireless for about 2 years now, because we thought that blockchain as a decentralized system presented a good opportunity to allow collaboration of networks. And we started by looking at existing shared access technology, existing models where networks collaborate or access is spread across multiple independent networks to see if there was ways that we could use blockchain to improve upon these. And these are systems such as Bluetooth, Wi-Fi unlicensed spectrum, television white space, and similar access models. In these cases, these systems, if either share spectrum directly or there is a sparsity of coverage in systems such as Bluetooth, or there is priority and secondary users that make it difficult to deliver services on top of these accesses or guarantee uniform or and universal coverage. So because of this reason, rather than pair blockchain with these systems, we specifically look towards 5G and pairing blockchain with 5G. Part of that is because 5G systems are macro cell environments. They're built for blanket coverage across wide regions. In many countries, there's multiple providers, so there's a natural redundancy of this coverage. And the 5G network structure supported things such as resource slicing, dynamic orchestration, modularity of network functions, and operating virtual environment and virtual overlays. In the case of MVNO networks, these are existing structures that we didn't have to recreate. We were able to start at that point and see if we could add blockchain to this to decentralize these virtual service deliveries, decentralize the slicing, decentralize the virtual overlays. So we had some difficulty with blockchain in the beginning. We looked at existing systems such as Ethereum because it has a robust developer community, it's open source, and it's quite familiar within the research community. But Ethereum, for example, had other dependencies that it bundled because of its use as a digital currency. So because the digital currency, the balances are dependent on the previous state, this record has to grow in perpetuity. Ethereum also guarantees its security through this record growing in perpetuity. So you cannot split the record or have a small chain, for example. Otherwise, it's easy for enough compute power to overwrite it. So we said, okay, well, we set aside Ethereum. What does it look like if we build our own blockchain that's specifically built to operate how wireless networks operate? Because we can't take an ever expanding record and package it as a network function. We don't have enough control. It's quite rigid to be dynamically orchestrated, spun up and retired, allocated storage on a fixed term or assigned a fixed life cycle. And we also had the problem that data in IT systems is living data. There might be data retention requirements where the data has to be retired after a certain period of time. So the wireless environment was an example where it was difficult to use a system such as Bitcoin or Ethereum because these structures required behaviors that conflicted with how 5G networks operated. So the way that we got there, we started designing our own blockchain system for 5G networks, and we needed to change the consensus model because proof of work, proof of stake, these depended on the currency ledger model. So we chose Federated Byzantine Agreement as the consensus. This is borrowed from the Stellar Consensus Protocol and the Stellar blockchain. So that system guarantees safety and liveliness. So it guarantees that all nodes reach a consistent finality in sequencing of the ledger record, and it guarantees that the nodes can reach finality and reach a consensus even if nodes become unresponsive or stop or are faulty on the network. So the way that that consensus works looks as the image shown in this slide. The idea is that the consensus is federated, and this is what makes it permissionless without requiring payment to control incentive and bad behavior. So in the federated consensus, you have groups of peers, networks in this case, that they have peering with each other, they reach a consensus agreement, and you have peers here that are peered with each other, reaching consensus agreement. If there's any amount of overlap between these two groups, the consensus reached here that includes that overlapping node must be the same as the consensus reached here because they share at least one or more nodes that have to agree. So the consensus on both sides needs to be the same for that node to have a single consensus. So by doing that, you can make the system permissionless so that it can federate outward in the way that networks peer. So you have your peers, but you don't control the peers of your peers and the peers of their peers. So this consensus can expand without any sort of control of membership or any restriction in this way, but the system maintains uniform consensus and finality. And so this model was chosen because it works much closer to how network peering operates. It works much closer to systems such as BGP, where you have route tables that are maintained by the updates you receive from your peers. The system is permissionless, but it's not trustless. So you don't control the updates coming from peers of peers, but you trust your nodes that you peer with that they're sending you correct records. So it's permissionless but not trustless. So outside of the core consensus, the CoNTe blockchain works more or less similar to systems such as Ethereum. The name CoNTe comes from a concatenation of core, network, temporal. So the CoNTe blockchain is designed for core networks and the policy orchestration at the core. And it's designed to be temporal. So it's not intended to be expanded in perpetuity. It's intended to be allocated in a manner similar to network functions or directly as a network function with an intended life cycle for an intended purpose. So you can spin up microchains for the policy and charging function. You may collaborate with a certain number of peers for a period of time, for example, the Olympics. You may have a certain structure that you collaborate with peers, you spin up a ledger that is immutable, that is decentralized for that one purpose, and you retire it. So this is a core network blockchain that is temporal. The protocol messages are quite similar to existing models. In the case of the proposal of new blocks, this follows the three-way handshake borrowed from TCP. So the proposing node proposes out a block, receives an acknowledgement, and then sends a final commit to its peers. And this is what that message flow looks like. In the context of this federation, rather than node 1 sends to 2 and 2 responds and they complete this between the two of them, when node 1 sends a proposal, node 2 sends it to its peers, node 3 and node 4, and it federates out until the edge of the graph. So node 2 doesn't respond until it has received a response from its peers. So it forwards all the way out to node 5, which is the edge of the graph. Node 5 has received it from everyone that it peers with. It has nowhere to forward it. And it responds to acknowledge. And that federates forward until the consensus ripples through the network back to node 1. And then the commit is carried forward in a similar manner. Because we don't control how many devices are in participating in the consensus, we needed a method to control congestion and contention. Who can commit a block at what time? Again, we borrowed behavior from wireless networks, Wi-Fi in this case, and we borrowed the carrier sensing mechanism from Wi-Fi. So the nodes in the CoNTe protocol operate on a exponential backoff timer. So within a range of backoff time that they're supposed to wait, each node has a random timer that's counting down until they're allowed to transmit. If they receive a block in the period that they're waiting, then they pause their countdown, they complete the consensus, and then they continue the countdown. So this system allows the graph to scale to unknown sizes while still operating consistently. In the case of very high density or very large graph, this can be tuned by choosing the minimum backoff period rather than zero. If you have very long delays, you're collaborating with a partner in another continent, you can increase the minimum wait based on the known network characteristics and tune this. Assuming an outlier case where the minimum wait period is misconfigured or not configured, or the delays are so extreme that you have node 1, it is in an outlier case possible node 1 initiates a commit block and it begins its ripple forward, but some peer of a distant peer also reaches their time or timeout before they receive the block and they issue a commit. So this is what that outlier case looks like. In this case, node 4 receives both. Because the nodes are using a globally synchronized time clock, node 4 can see the timestamp of when the transactions were issued, and node 4 resequences it, and it forwards the original block 1000 to node 5, but it modifies the block sequence because it knows 1000 came first, and it makes that other block 1001 and continues forwarding it, rippling it forward in a new proposal. And these proposals are allowed to run in parallel, which is quite efficient. And this works because the network is trustful. You trust that your peers are sending the correct information. So in the case of node 5, it receives that block 1000, which is not its original, and it receives that block and hashes it to its chain. Its aggregate hash is now changed. So when it receives an acknowledgement on its original block, it also sees that its block is block 1001. And so it updates on its side the final valid hash value. That aggregate hash also gets updated, and then the final commit goes out so that the record can stay consistent across all nodes as the consensus federates. So now we look at performance. We ran the simulation of this protocol at 1,500 kilometers, roughly the distance between New York and Los Angeles, 15,000 kilometers, Los Angeles to Singapore, and then we wanted to see, okay, what about small cell environments, even though the system's intended for core networks? So core network being data center, maybe you have a cloud core and you have Seattle and New York, or Hamburg and Paris. You're deployed within AWS. So 150 kilometers isn't typical, but we wanted to see what that performance looked like. So we have the numbers here of scaling. 1 block per hour, 1 block per minute, 1 block per second. At 1,500 kilometers, we can see that the system starts to degrade and the efficiency at 1 block per second the system essentially starts to collapse under the extreme delay. Los Angeles to Singapore, for example, this is quite an extreme network delay. And the system assumed that each node was equidistant. So it's 15,000 kilometers, 15,000 kilometers, 15,000 kilometers. So these are quite extreme aggregate delay in the system. So the system starts, it cannot quite support 1 block per second at such delay, but 1 block per minute and 1 block per hour, these rate of updates are performant in the design. Then finally, we go to small cell, one in, let's say, metropolitan network. This scales quite well, relatively linear to 1 block per second. So we wanted to see at what point does the system degrade. So we scaled up to 50 nodes, which wouldn't, 50 core networks or 50 hops of peers, this is not a realistic scenario, but we wanted to see the edge of performance. And so at 50 nodes, all submitting 1 block per second, the peak reaches almost 28,000 updates in an hour, but then it starts to degrade from that point. So to put in context, this rate of updates, how it compares to Ethereum and Bitcoin, the CoNTe design is quite a bit slower than these other systems. So in this case, we are taking the trade-off of this exponential backoff timer to guarantee congestion avoidance. We're taking this network-centric design as a compromise versus sheer performance and under the mechanisms of how systems such as Ethereum or Bitcoin operate. So the system's quite a bit slower, but it is temporal. It can be packaged as a network function. It accommodates permissionless operation and scaling out, but fits within the trust model of how networks operate. So we give a trade-off of one and give up sheer speed. So that is the summary of the research to create the blockchain for network 5G networks. And so the assumption is that with this design, you can then start to share information that allows you to allow access for the same device in multiple independent networks, or allocate the same amount of bandwidth for emergency services for all networks, or for example, make as a condition of licensing a spectrum block that certain public utility services need to be made available. So this sort of scenario is now possible when the information needed to build these overlays can be agreed upon, decentralized, and updated in real time without any central owner. This makes delivering these sort of services pervasive road connectivity, for example, pervasive disaster recovery, emergency services access across any carrier working the same regardless of country. It makes this level of collaboration possible. The biggest caveat being IP mobility and direct handoff. So there's still a gap in figuring that out, and that's where we are targeting the next phase of research. The current proposal looks at a system named Host Identity Protocol from the IETF is a suitable application here. It substitutes the IP address as the addressable destination with a new host identity. So the IP address can change as the device changes networks, but the DNS routing happens application side. So the application gets updated with an IP address tied to that host identity, so it now knows where to route the transactions. So that's pretty much the presentation, and thank you. I hope that this is an interesting perspective of blockchain, or what's possible with blockchain when it's designed from the ground up in the context of carrier networks. I did want to put a last note that there's multiple, but there's a IEEE working group that's working on a standard of sharing information across carriers, telecommunications data, specifically for pandemic response. So this same idea of public utilities, disaster, emergency, health response, these type of services are the classic model that would fit this type of collaboration. So if you're interested in attending these meetings or have similar research or want to share ideas, you can contact me to connect for these sessions as well. Thanks again for joining the presentation.